So this begins our section on vibrations. This is chapter 8 in the book, and I kind of typically group it into 5 lectures. So first 33, where we're going to talk about free vibration of a simple system, and second 34, where we're going to add damping. And almost all systems have some amount of damping, even if you can neglect it in certain cases. Then we're going to talk about force vibrations, which means if you want to keep the vibration going, you have to keep adding a force and keep pushing it. And then we're going to think about vibration for other types of rigid body problems. And then we're going to look at energy methods for vibrations. And what I like about doing vibrations at the end of dynamics is then we kind of get a chance to go back and look at some of the types of things that we've been talking about, like energy and rigid bodies, in the context of vibrations, and look, and kind of, it gives you a review and also a little bit points to some of the graduate class vibrations that you can take as an elective, as a tech elective, if you like. All right, so let's begin. This is going to be step 1, finding the equation of motion. It's kind of a messy end. Fix that. Finding the equation of motion, which we sometimes also call EOM. All right, so for every vibration problem, we characterize the problem by getting it into for without damping, we get it into this format. We have some kx term, and we have some mx double dot, and then when it's forced, we're going to have something non-zero here, but for now we're going to start with 0. So, but this is the simplest vibrating equation of motion. We have some mass and some stiffness, and this is the position and the position derivative twice. All right. So typically, what this will look like, like the simplest possible vibration problem, is going to be a spring here attached to a mass. All right, and so we're going to have some stiffness of our spring K, and of course this mass, we'll start with it having some mass. And we're going to define how this moves by setting up a position descriptor. And I'm going to call this Y for now, because I know what I mean. Y is displacement from unstretched spring. All right, and we know that eventually, if this is on Earth where there's gravity, after we let this go, maybe it bounces a little bit, but it's going to settle at some new position here. Where now this is going to be some delta that is going to represent how much the weight stretches out the spring. So, all right, let's start with our free body diagram. All right, so if we draw a free body diagram from the unstretched position here, then we're going to draw all the forces, draw mg, the weight, and then if it has moved to some small y, then we know that if it's moved positive y, then the spring force is up this way. So we can draw ky here. And these are the forces. So we want to define the acceleration in the positive y dot terms. So we can say sum of the forces equals my double dot. So that means we want the positive forces to be in the direction of y double dot, which is going to be in the direction of y. So that means mg minus ky equals my double dot. All right, so this is good. This is an equation of motion from the undeformed position, and if we rewrite this, we can write K. Actually, I'm going to put the I like to put the M first when I write vibration problems. So put this on this side, and then we can get our Ky, and that would equal negative mg. All right, so, but this equation isn't quite the one I showed you that we want, where we want to have 0 here, but we can change it into an equation that does have 0 here, so that by looking at a slightly different variable, let's look at this variable here, x. So y is from undeformed, and x is from equilibrium. Okay, so now we can write that the total displacement away from y, you can say y is going to equal some delta plus x. And now we can show what this delta is because it's the equilibrium. So it's when y dot dot equals 0. So let's do k first. K delta equals mg. So that's just from setting this y dot term equal to 0. So now we can show that this delta is going to be equal to mg over k, which means now we can say y dot dot is equal to x dot dot, and now we can change, because but just taking, like, obviously this isn't, this delta term is a constant, so this isn't changing. We take the derivative of this once, y dot equals x dot, but we take it again, y dot dot equals x dot dot. So now we can change our formula here, and I'm gonna give us some space for that here, where we're gonna say, now x dot dot plus k delta plus x equals mg. And now if we substitute this delta here, so we've got mx dot dot plus kx plus the k's will now cancel. We'll get mg equals mg. These will cancel, and we'll come back to mx double dot plus kx equals 0. So this is the form of the equation that we wanted. Originally we want to have nothing here and this x double dot and this x here on the same side of the equation. And also you notice that they're both positive, and they better be both positive or else it won't be a vibration problem. So that's an indication that you've done something wrong if one of these is negative on the same side here. All right, so that's for this pretty simple problem. But we can get where we can get to this from the equilibrium position. And I hope that this convinces you, though, that you can always do the free body diagram away from the equilibrium position. You don't have to start with doing it from the undeformed position. You want to start with doing it from the equilibrium position, and then thinking about the forces that would increase as you move away from equilibrium. So when you draw, if you now you see this spring problem, again, and you're going to go to draw the free body diagram in vibrations, you're going to draw it from x. So you're going to move down x, you're going to have an increase in force kx. But you're not going to increase the weight. So the weight isn't going to change. There's always going to be some k delta and some mg, and they're always going to be equal and opposite. So you don't have to worry about them. And this is the case always if the springs are linear, which will be always for this class. We can always start at the equilibrium and take the free body diagram about the equilibrium. So let's do an example of that for a slightly different problem. Just like a little bit more involved, but still no damping. Let's see if we add a pulley here. Maybe I will draw the problem in this corner this time. So imagine you have a spring here, and then this spring wraps around a pulley like this, and then this pulley comes up to another pulley. And these cables are fixed to some like nice rigid beam because we don't have to worry about that moving or vibrating. And so this pulley, maybe it has kind of this metal piece here, and from this pulley hangs our mass. And this spring will have some stiffness K. All right, now we want to find the equation of motion for this system, and we want it to be in the form some equivalent m, some equivalent mass, times x double dot, plus some equivalent spring times x. But we don't know exactly what the equivalent spring is. It'll be related to this K, but let's find out what exactly that is. And we do that by drawing our free body diagram. So let's start by drawing a free body diagram of the mass. So here's our mass. And let's define some displacement x down. And then there'll be some force up. And so we're going to have our mx double dot is going to be equal to negative of whatever this force is. Okay, so how do we find out what this force is? Well, we can draw a free body diagram of this pulley. So we can draw this pulley. And this pulley is going to have some force equal and opposite to this force. And then it's going to have some tension from these cables. So we're going to have some tension here from this side. We're going to have some tension here. And we're going to have some tension here. And pretty quickly, we should be able to argue that these three tensions are all going to be equal to each other. So T1 is going to equal T2. So here's T1 and T2. Because if they didn't, then like this would have to be, this would have to have some angular momentum. And it can't because we're assuming all the pulleys are massless as usual. So T1 has to equal T2. And then similarly, T2 has got to equal T3 because if this was more than this, then this thing would have to have some change in angular momentum, but that's impossible because it has to have zero angular momentum because it has zero moment of inertia because it's massless. So as which I think we discussed when we first talked about pulleys, but see, vibrations, so good for review. These two tensions are going to be equal. So there we go, we've got all of our tensions set to equal. So good. And now what are those tensions going to be? Okay, we know so that means that negative F is going to be equal to, so if we write this out, we can write T1 times 3 negative, because that's up, all of our positives are down, plus F is going to equal 0, because we're not allowing our pulley to accelerate either. Again, there's no mass here. So that means that it's going to be negative 3 times whatever T1 is. All right, so let's keep going. What is T1 going to be? Okay, so the tension here is going to be related to whatever is the deformation of this spring, K. So we need to think then about the length of that spring and how that spring is deforming. Which means now we need to think about the total length of this whole thing. Let's say, we'll call that capital L. And then we'll think about lowercase l as being this distance. All right, so the tension here which is going to be the tension everywhere in the cable, has to equal the change in the total length of the cable times K. Now, the total length of the cable is going to be related to, like, okay, so one little L here, and then it goes around the pulley, which is going to add more to the cable length, but it's not going to change. So we could say L is going to be equal to little L plus cable around pulley plus little L plus cable around pulley plus little L again. So that means that the change in L is going to be equal to 3 times the change in little l, because there's 3 L's here. So when this L increases, that's really going to stretch this spring 3 times as much as however this increases. All right, so it kind of took a long time to get there, but I hope that makes sense. Feel free to ask questions in the discussion. But okay, so now we know that the tension 1 is going to be equal to three times the change in L. But if you look at this change in L, however much L changes, this displacement from equilibrium, x, is also going to change. So 3x. All right, so we can now put this equals 3 times 3x. All right, so now here at last, if we look at setting mx double dot equals 3 times 3x, and then we just rewrite that. We can write that this system has an equation of motion in this form. Mx double dot plus 9. Oh, I forgot the k. There should be a k. Kx 9 kx equals 0. Right, because it's going to be whatever that displacement is times x. So the equivalent stiffness for this system is going to be not just k, but 9k, and that's because of how this is set up. All right, so once we have our equation of motion into some equivalent mass times x double dot plus some equivalent stiffness times x equals 0. We're ready to go into the next phase, which is solving this problem.